thought there's two people on thermo.
Yes, two. There's one. I'm the only in-person one, and the other individual I believe is from Sheridan.
Oh.
So it's a multimodal situation. Yeah.
All right. Last time we left off, we were looking at some scope field, direction field plots. We're going to look at some more of that today and add a little bit of terminology. Specifically, our equilibrium solutions. So in order to do that, let's look at a very, very common example, the logistic equation. All right, so this is the standard logistic equation for growth. All right, we have some constants in here, not going to be the point. The important one is K, which is the saturation level, aka carrying capacity, which brings up a fun tangent for humans. Where are we on the growth curve for humanity? Does anyone know? What's it look like?
Like in the sense of the population growth?
Yes.
Is that what you're asking?
World population growth.
It's like a huge exponential curve.
Yeah. What will it eventually become?
Flat line.
Logistic, right? It should eventually end up and be this, all right? But we are currently here, right, on the spectrum, and we're not sure what this gap is, okay? So by definition, right, there is only one planet. There is a maximum. We just don't know where it is. When the curve, because the curve is currently, for humanity, it is concave up. Eventually, it has to become concave down. So, just fun fact.
So theoretically, there's no straight line asymptote that's everyone try to approach.
Yes.
Okay.
Yes. No,
okay.
No. Yes. I mean that's what this is what a logistic curve is. There is absolutely there is an asymptote.
I don't know if it was eventually supposed to curve down and then kind of isolate because of like being in some kind of like harmonic motion.
No. You're absolutely correct. Okay. Logistic curves have a horizontal asymptote at 0, right? Because all population is 0, right? And then they have one at whatever this value, this carrying capacity saturation level is.
Okay.
Yes. We just don't know what that is because we don't know what. Yes. I mean, yes, I see what you're saying there.
Yeah, I see if it eventually curves down because like you exceed your capacity.
That was just how I do
it. Okay.
So to look at an example and exactly what we were just talking about. So if I throw in some values here, all right, for a saturation level of 10 and, looking at something like 10 million. What happens when we do the direction field, okay, we have our horizontal asymptote here at 0, and we have it graphed below because everything will go away, all right? And then, all right, at 10, so even if you have a population above this 10 million, notice, right, because this is the saturation level, that's the carrying capacity of this situation, that if it starts above, the population can't support it, and even those head towards the horizontal asymptote, all right, that exists, all right, at 10 here. Also, right, we could easily solve this just like we did last time, right? Set the derivative equal to 0, and I would get p equals 0 and p equals 10 with these solutions, right? So just like we did last time, we want to identify the horizontal asymptotes, all right, because we want to see what the direction field is doing. But logistic curves have a very, very interesting one because populations grow to fill their area and populations decrease, all right, to meet the needs of their area. All right, a population that can only support 10 million, it can't survive on 14 million for long. So logistic curves are used for all population growth within a fixed region. And Earth eventually will be that, right? One planet. So there is a fixed region of how much that can support. Again, the big thing without a doubt is the value K, the carrying capacity saturation level. With all logistic curves, we're going to have that. All right. And you can always identify because, all right, the curve above it will decrease to it, below it will increase to it. All of this is basically what we did with direction fields last time. The new part, all right, is this definition of equilibrium solutions or equilibrium points. Typically, we call them solutions because it's not just a single point, it's a whole line, right? So we saw the three things that were happening, and they were all existing around the solutions to our differential equation. All right, 0, 10. So below it, all right, everything decreased away from that value. All right, between 0 and 10, it increased to 10, and 10 to infinity, it decreased to 10. This creates three types of equilibrium solutions. Unstable equilibrium solutions is when all the curves move away from that horizontal asymptote. Asymptotically stable asymptotically stable equilibrium solutions are when everything moves towards it, right? Like our 10. And then semi-stable is where one side is moving towards it and one side is moving away from it. So, all right, back to our situation here. So here, right, both curves, whether it's above or below, are moving towards it. So our solution, all right, the curve P equals 10 is asymptotically stable. P equals 0, notice that everything's moving away from it. This is moving away from it, that's moving away from it. So that one, P equals 0, is an unstable.
Excuse me, though. On the right-hand side, should that be P equals 10?
Oh, 10. Yes, thank you. And so this is just extending off of what we did with direction fields by identifying long-term behavior. We can also identify what kind of equilibrium solution we have. So it just adds another factor to what we're going to look at. To that end, all right, I want to find and classify all equilibrium solutions for this differential equation and identify the end behavior. So we're going to look at what we did last time and add this new definition. As always, we need to start by doing what? With our differential equation. So 0 equals 0. Nothing novel, nothing crazy. That gives us the values, all right, -2 and 3. And then, all right, now we need to start plotting in points to create our direction field, right? Start picking points and we're going to create our direction field.
Using GeoGebra, we're using by hand.
Or if we could use the technology.
I was gonna be like, are we not? You're not gonna make us use by hand, are you? Like,
what was it? What? Squared something?
minus y minus 6.
Squared minus 1 minus 6.
Did you all do this by hand, Beau? Back in the day?
No.
Okay.
I was like, actually, I don't know. I felt really lucky at our school. Our school had a subscription to Maple.
Oh, cool.
And so we actually just, I was like, we were actually, like, they had student versions that they gave us.
That's sweet.
Okay, so okay, actually -5 and 5, we can actually leave it as such. Let's find another one of these. So, all right, we can identify, all right, our long-term behavior. So we have our points, all right, exactly as we found, -2, all right, and 3. All right, at -2, I see that this one is going towards it, this one is going towards it. What kind of solution is y equals -2?
Stable asymptotic.
Asymptotically stable. Yeah, no, that one we say asymptotically stable. The other ones we just say unstable or semi-stable. So, all right, asymptotically stable here, all right, as well as, all right, identifying our end behavior. All right, so any starting value from -infinity up to and excluding 3 all head towards
-2.
-2. All right, and then what about y equals 2? 3, y equals 3.
Repeat that, I'm sorry. Where y equals 3.
What kind of equilibrium solutions?
Unstable.
Unstable. Everything's heading away, and so hence at exactly 3, it's going to head towards 3, and then everything above 3 heads towards infinity. And again, just like we did last time, just adding a definition here. Let's see, end behavior. That was all the way up to, but excluding 3. Line t heads towards -2. Exactly at 3. Let's write that.
Do you have to add the equilibrium solution for it to be considered correct?
Say that again.
When you're defining these,
Oh,
is it sufficient to say?
Because when you say asymptotically stable, obviously we're talking about equilibrium solutions. I mean, that's probably.
I just didn't know if you would knock us, I just want to know so I know what to do.
I probably won't, but you should.
I probably won't.
I was like, get in the habit of.
Okay, I'll just.
Because it's that term equilibrium solution that is like the key, but it literally asked for it.
We ought to put non-equilibrium solution. Oh, okay.
What?
I see you. Okay. An unstable equilibrium.
I was like, that was everything from the picture. I already forgot. Okay, let's see. -2 was asymptotically stable. 3 was unstable. All right, and then it was -infinity all the way to 3, excluding went to -2. Yes. I was like, jumping back and forth this morning. All right. Oh, and then that also reminds me. So just make sure that you have all the values included, right? I'm covering everything from -infinity to +infinity. Did we miss any numbers?
I don't think so.
We got them all. The biggest one is this one, since there was only one, but sometimes like you'll have 2 less thans and you'll forget the values. So just always make sure that you have all values, all starting possibilities, -infinity to infinity covered. All right, let's do just one more of those, right? Yeah, just one more. Once again, set our equation equal to 0, our derivative equal to 0. let's see, y equals -1 and then -2. -2, -1, +2. Nothing difficult to those solutions. Let's see what that looks like.
Whoa.
Okay, this is just I'm glad that actually it did this because this is just a downside of the technology.
Okay.
Obviously, is that actually happening?
I hope not. I mean,
No.
okay, I was like, what's going on here?
I was like, this is, and it does all kinds of crazy stuff. So that's why it's super important to move these around. I was like, yeah, because it just does all kinds of weird stuff.
Huh.
Yeah, and actually, see, it's even having
No.
it's even having a hard time identifying
The asymptote.
because right here at 2, and this is why we have to solve it first, right? Because I know -2, -1, 2, right? So I know stuff's happening at those, and so I have to figure out what's happening. And the technology is not perfect, right? But it is free. So it's always, I was like, gotta always make that trade. Okay, so let's start right at the bottom here. All right. Okay, so -infinity up to -2. See, and that's why we got to make sure that we identify what's happening at every single stage. -infinity, all right, up to -2, actually all the way up to -1. Let's bring this one back. Let's bring this one right there. So, all right, starting with our end behavior, -2, all the way up to what heads towards what value?
All the way up to -1, heads towards -2.
Okay, so we at least got that end behavior. Let's do some pieces this time since -infinity less than 0 up to -1.
Excuse me.
All right, and then what kind of solution is -2?
Asymptotically stable equilibrium solution.
Okay, so now we are
Need one more solution. Okay, he was gonna do that. That's cool.
move that one there. Okay, so all right, now we're at -1. Okay,
2.
so -1 all the way to 2 heads towards -1.
What that one doesn't though. The other one goes towards infinity.
Okay, this is the weirdness of I had it on there
I'm sorry. Then.
right at the.
Okay.
I was like, where? So it's good, just so you know, because your homework problems are going to do this too. All right. So if this is further up, like it does weird stuff, like so. But obviously, this one can't get fixed. Yeah. So notice this is technically above this asymptote, right? But even if it was there, you just have to know it's above the asymptote. I was like, because there's no way it would pass through an asymptote, by definition. So,
Where were we?
we were
From
at
one
-1.
to
All right, -1 all the way to 2 heads towards
-1.
-1. Including anything? Is -1 excluding or including? Do you see what I'm saying?
Yeah,
Let me write it out.
Be
so
excluded,
you can see.
right? Because it has a,
-1, y0 all the way to 2, y(t) heads towards -1. Like that?
I think so. It seems to be correct. And then we gotta put the,
Nope.
it's
We're missing one little piece.
the asymptotically stable part, or we asked,
Remember when we just did this one, right? Y0 of 3 heads towards 3.
so
y0 of -1.
Well, do I add that in or can I just do one little thing on here?
7 equal.
do an equal sign under that.
Yeah. So remember, we have to include all the values because, I mean, yes, they're quote an asymptote, but they're actually touching that value. They shouldn't be passing through it. They should be ending on it, you know, like, so remember, we have to make sure we include all our values. Because always at minimum, y0 of -2 hits -2. y0 of -1 hits -1. That value that we found those asymptotes for, they have to hit, all right, that value. All right, then let's do the stability of the equilibrium solution. Okay, so just for -1, and obviously we're doing this as we go, but you can do all the equilibrium solutions and then all the end behavior. We're just bouncing back and forth, whichever is easier. So, what kind of equilibrium solution is -1?
Stable.
Semi-stable.
Semi-stable. This one's going towards it. This one's going away from it.
Okay.
All right. When they're both going away, unstable, both going towards stable. And then, oh, look, we got the halfway, one towards, one away. So that one's actually semi-stable.
So when you're comparing these things, you have to look at the picture as a whole, not just that one little section.
Well, I mean, I am looking at that one.
I know, but so like, when we have the first part, so like, we concluded that the y or negative infinity to -1 was asymptotically stable equilibrium solution. Because all these things converge to -2. How come that's not semi-stable? Because of all these other values that are on there.
But because everything below -2 is heading towards -2. Everything above -2 is heading towards it. I'm looking at just this piece. Is that what you're asking?
Yeah.
Oh, because like this one's not heading towards -2. Yes, you're right. You look at each piece of the horizontal asymptote.
Okay.
So yes, that's why I moved this one because I only need to see what's above and below -1 right
Okay.
there. And this one, I only need these two.
Okay.
So you're absolutely correct in that regard. Yes. I don't look at the whole thing because yeah, not everything is headed towards -2. Only what is directly below it and above.
Okay. Thanks for that.
Yeah, so okay. So that one's semi-stable. All right. And then lastly, okay, so we're now at 2. So at 2, okay, we had already gotten all the way to 2. And so basically exactly at 2, what is happening?
It's a hard asymptote, right?
Yep, it's headed towards 2. But then everything above 2 heads towards infinity. Best as we can get on our picture, right? So that's the part where we have to make sure we have those values. So now we have to separate this again. Y0 equals 2. Y of t heads towards 2. But then everything from 2 infinity heads towards infinity. So that, again, we'll have to make sure. The biggest thing is leaving one of these out, and that's the thing I really focus on because I want to make sure you have all the values. All right, and then lastly, y equals 2. What kind of solution is it? Unstable. Unstable. Everything's headed, right? Headed away, headed away. All right. And again, don't get hung up on that So again, basically the same stuff we looked at last time. I was like just adding a little more definition. Just practice. All right. Okay. We actually now are going to solve the most common type of differential equation, all right, with the most common technique, what's known as integrating factor. Without a doubt, all right, all the way to the end of the class, we're still going to be doing these because it just occurs so commonly. Everything about Diff Eq is form, though. So when we get these, when you identify, oh, it's a linear differential equation, all right, and let's just refresh there, right? Ordinary or ODE or PDE?
OD,
ODE, why?
because there's no partials.
Because there's no partials, yeah. I was like, not a trick question. I was like, all right, and then why is this linear?
Because there's nothing above first power.
First power in what variable? That's the important part.
Why?
Y, okay? All right, nothing about first power in Y. Could there be stuff, cosines and exponents in T? Absolutely, and there will be, all right? The fact that this is linear has nothing to do with, well, when you look at the whole equation, that's not linear, okay? It's about the variable we are differentiating, okay? With a variable we're differentiating with respect to, that can be a total disaster, okay? Okay, so that's linear differential equation or ordinary. So the integrating factor technique, basically identifying this piece and then we multiply it all the way through. Now, most of the time, I don't do the proofs because I'm not a pure mathematician or applied mathematician. But this one, all right, because it's so related to how we actually solve these, all right, I'm going to do it here. And this is just a really, really fun proof. And gets us a little bit more practice with identifying the differential equations and messing with them. Also, because there's so many reasons, obviously. Want to make sure that we understand everything that's happening within this equation. Now notice a lot of times we just write this as y, but this one I want to write as y of t because we have a lot of stuff going on. So the concept of integrating factor, multiply the differential equation by the integrating factor. This is the whole concept of what the integrating factor technique is. Okay, so we multiply that through and we have a big old mess of a bunch of things that we don't know what they are, right? Mu of t, p of t, y of t, g of t, all right? All of these create giant functions. In order to simplify this down for us a little bit, let mu of t specifically mu prime of t equal mu of t, p of t. Now, the interesting part is right here. This, okay?
Chain rule.
Oh, no, close, so close.
Yeah.
Not chain rule.
Course.
That's the product rule. Product rule. First derivative of the second plus the second derivative of the first. All right? That's actually the product rule, which means I can actually rewrite that as the whole thing, all right, to, all right, the derivative, right? Mu of t, y times y of t prime, all right? That's what that actually is. So that means we now have, all right, mu of t, y of t prime equals mu of t times g of t. Then, all right, when I have a derivative, how do I get rid of it?
Take an integral.
It's integrate both sides.
When we're doing this, do you want us to show the dt moving over to both sides and then do the integral, or, you know?
The dt.
So like when I was taught doing this kind of stuff, you have like d over dt of this function, you move the dt over, then you.
Oh, no, we don't need to worry
Okay.
about that. It's all, this is all with respect to t.
Yes, sir.
I was like, because also, if you move that over, you have d, you're integrating with respect to. Yeah, no, this is d dt. You move that over. The problem is this side needs to be integrated with respect to t as well.
Okay.
We're doing d dt
Okay.
to both sides. Yeah, you don't.
No, I see.
Okay. There's dy dt. When you move that over, this side integrates
Stays
with
dy.
respect to dy.
see.
This side integrates with respect to dt.
Okay.
That is one technique of how you integrate.
Yes, sir.
But here we're
In this
doing
case.
both sides with respect to dt. So
Yes, sir.
that this is more of like almost an algebra concept. What I do to one side, I do to the other. Integrate both sides, right? Let's specify that. Integrate both sides. To t. So over here, this one just drops away because integral of a derivative. And then we have a plus c over here. And then I can move it to the other side because I don't want it on this side. And then also, I move it to the other side, but again, because we are doing, it is any constant, doesn't matter if it, did I just said plus c on the other side? Just make sure, right? So even though, yes, you subtract from both sides, but I subtracted a unknown constant, so it doesn't forget. And then, all right, remember our overall goal, we are trying to solve for y. So I'm going to divide by my integrating factor here. Now, be aware, this gives us one big result. This is the overall concept of the integrated factor, but we want to go a little bit further. This result also isn't actually that helpful to us, right? What is super helpful is remember how we got there. We assume, right, that mu prime of t equals mu of t p of t. If we solve this over, I want to solve this for p of t instead. When I solve that for p of t, does this look like something that's familiar?
Motion.
Nope, nope.
Okay.
Even simpler. A particular function. What function? You end up with a function in the denominator, then you have to take the derivative back in the numerator. It's natural.
The log. I see you. E.
Well, yeah. I mean, well, ln. Just the derivative of ln, right? Ln of 7x becomes 1 over 7x, 7, right? Like, you take the derivative, you just do 1 over the inside of the log, and then take the derivative of then you do chain. But basically that means this is actually just ln of mu of t. Lots of parentheses. The derivative of that. So that's just another way to write that exact same thing. Now that's really useful because when we go to actually solve this, now I want to integrate both sides again. Because now I want to find if there's something, what we're trying to do is find something explicitly helpful to us that we can find in each case for mu of t. And that's where, of course, we're going to end up. Once again, I'm going to move that to the other side. And then, all right, one last little step. Remember, I want to solve for, now I'm trying to find what mu of t is something useful. What do I need to do?
Find something that cancels out the natural log.
Yeah. What cancels out a natural log?
E.
Specifically, so I just multiply both sides by e?
You gotta set E into, for T, right? You plug E into the value
You
of
gotta
T.
set
or-
it to power.
Yes, we have to create an exponent. Now, technically you can use the definition since this is log of e, it becomes e to this equals this, right? That's the definition. The algebraic way of saying it is we raise both sides using the e power,
Okay.
right? E becomes the base and both of these become the exponent.
Okay.
So just so you know the algebraic way of saying that, but technically you could just use the definition e because it's literally this to the this equals this. That's the literal definition of a log when you have 3 pieces of an equation. All right, but right. So basically, raise both sides to the e. E to the natural log cancels out. I have mu of t equals e to this whole fun thing here. And then let's simplify this just a little bit. All right. Just remembering our rules of exponents, this actually becomes e to the pt dt e to the c, which actually then just becomes e to the c is yet another constant. Let's switch it. Let's call that a k. And so I actually identified an integrating factor that is useful to us. One last step, because I have this constant here. Let's plug this back in. Plug mu of t back into y of t that we found above. All right, so our y of t that we previously found looks like this. All right, now let's actually plug in our mu of t. And I'm doing all this just to show one last thing. All right. So we got this, have an integral inside an integral here, right? I mean, this thing is okay. But this constant k, if I'm inside an integral, what can I do with that?
Take it out.
Pull that out.
Pull it out the front.
All right. That can actually pull out, which really leads me to be able, if that comes out and I have a k there and a k down there, that will cancel in that one, and I end up with c divided by k here, which c divided by k becomes
Another constant.
Oh yeah, just another constant, so who cares? All right, so that means that we can actually cancel that. That leads us so we don't even have to worry about what that constant is when we identify our integrating factor. So the result is this. Y of t results in this, which is what we just found, where our integrating factor is e to the integral of p of t dt. That is super useful, and the constant went away. Okay? This is not super useful, but this, all right, finding that integrating factor, that's going to be, we're going to use that all the time. And that's really why I wanted to do the proof, because as long as we get it into this form, and notice, where's p of t, right? I need p of t in order to find the integrating factor. Where's p of t? Oh, look, I will always write it in the form because that right there is p of t. I'll do a quick integral, raise it to the e, and then boom, multiply the whole equation, and then we can just solve the differential equation down. And we're going to see how simple that becomes actually pretty repeatedly.
Just know, it's just some of those problems are not simple. Some of these are hard. Yeah.
I was like, here's the hard part. Just like, and here's why I did the proof as well. In every single one of these, we're going to need to identify the product rule. That might be the hard part, but that really is going to help you refresh on your derivatives of functions. Specifically, right? Well, the derivative of secant and the derivative of tangent, things like that. All right. We want that to be
Autonomous.
Yeah, like quick. So that's the only big thing. And then whenever possible, right, we're going to solve for the solution. Sometimes we're not going to be able to do it explicitly. We saw that already. All right. Most of the time we should be in the beginning for a bit. All right. Let's look at some examples. So let's go back to what is this? Does this look familiar already?
Use it last week.
Yeah, we
Air
did.
resistance and falling object.
This is our general falling object differential equation. All right, with a few constants thrown in there. So, everything, like I said, with Diff Eq is form. It all starts and ends with proper form. Okay, so good news, the form is almost there. Oh, and that reminds me of one other tricky thing with our form. So I got some stuff with T, I got some stuff with T. Notice what's right here. What's next to the derivative?
The P of T, is that what you're asking for?
The derivative. What's next to this?
Nothing.
Nothing, a one. Okay, so.
Like no constants or no modifiers, is that what you're asking?
Yes, exactly.
Okay.
No 5, no sine of X, nothing.
Okay.
Okay, so form is everything, because
Pure derivative.
if I don't get it into the correct form, I
That
just
don't work.
proved it. This has to be this form in order to end up with this integrating factor. So, all right, so I want it derivative plus some function times y. All right, so now, and we're gonna keep changing variables. So what do I need to do to get this into the correct form?
Change B to Y. And then add over.
I don't need to change it to y.
Just need to solve it algebraically first, right?
Yep, specifically what?
Add 0.1, sorry.
Yep. Add that over. dv dt plus 0.196 v equals 9.8. Simply that. Now we're in the correct form. Yes, you can change it to y if you want, but vy. And yes, now we have the form. P of t is this guy right here, so I can identify my integrating factor. And the integrating factor, all right, the good news is because these linear differential equations, this actually turns out not to be too bad off. Also, remember that integral is in the exponent. Just in the beginning, make sure you don't make that mistake. And now look, 0.196t. Do I need to make sure I add plus c on here? All right, this is an indefinite integral that I just integrated.
Should have the C included, right?
We do.
I mean, we don't have any parameters to even solve for C, so in this case, it's not helpful, but they do cancel out in the other one, but it was taken into account at the end of the integral because we still have that plus C at the end.
Yeah, we canceled it. You're absolutely correct. At the end of the integral, all right, this whole thing will have the plus C on. You're absolutely correct. The whole thing, all right? But for our integrating factor,
No C.
that was the whole point. We got this stupid K and we canceled it out.
Okay.
All right. Again, I was like, I don't believe in proofs a lot because it's just like
Tedious.
yeah, like but this one, because it is so related to the solving and linear, this simple linear differential equation, first order linear differential equation that this is, we do this one, we're going to do this all the way to the end of class because it's the most common by far. That's why it's in chapter 1. Okay. All right, so we got that guy. All right, then multiply the differential equation. dE by the integrating factor. So we multiply the whole thing by the integrating factor. As long as we identified our form and P of t correctly every time, all right? This should line up almost perfectly. You might have to do one little thing, but this is exactly what
Product rule.
That's the product rule, right? And I can see it right here. Now technically this is out of order, the V could be right there, but I was like, but this is the product rule. The derivative of e to the 0.196t, right? Bring it down, nope. And then derivative of v is dv dt. So this is the product rule. Then we just have to make sure we identify the pieces of it. And e to the 0.2t, right? And v, right? And then just always give it the quick check. All right, that derivative of that is that, derivative of this is that guy. All right. But that should basically every time be the product rule. And that's the part that sometimes people struggle with. But again, this helps you make sure you remember your derivatives. And then just like we did in the proof, now what do?
Integrate.
Integrate. Oh, 50. Becomes a self. And then just also one last step, just like we did in the proof, what do we need to do?
Solve and cancel out the e.
Yeah, solve for v. So divide both sides, or divide the whole thing, however you want to say it. Now, here's the big part, and this was in the proof as well. Notice, remember that whole thing was divided by the integrating factor in the solution? So, for the first equation, 50 e to the 0.196t divided by that is just 50. But that c, all right, actually needs to be adjusted. That becomes c divided by e to the 0.196t. AKA C E to the negative 0.196 T. Because this constant, all right, is actually dependent upon the integrating factor, which has a variable. That's not like we were saying, oh, it's constant divided by constant, still no constant. Not a constant. All right. That is now a function dependent upon T. All right. So, same steps as the proof. All right. Same exact steps as the proof. This is then, all right, what we were talking about last time. This is called the general solution. All right. Which last time I was saying, here's a general solution, we have it. Here's a general solution, we have it. All right. This is how we actually go to find it. To then to solve the IVP, we can then go one more step. All right. Now I have the general solution. Now I have my initial condition at V of 0, right? At time 0 seconds, the velocity was 48 meters per second, given that we had context for this. So I can actually plug that in to my general solution and solve it to find C. And we had a name for this one as well, the actual solution. After you solve the IVP down, which again is just plugging in the numbers. Then we get an actual solution, all right? A solution, actual solution, meaning a solution to a specific set of initial conditions. The last step is always the easiest without a doubt, all right? So a lot of times we're going to see a lot of cases where we stop at the general solution. It just depends if you have an initial condition or not. All right. All right. Let's practice these quite a bit because that's going to be the biggest emphasis that you're investigating here in this first section. We graphed some directional fields, but this, all right, this is something we definitely need to practice. Okay. So we talked about it before. Notice we have an interval of validity. A lot of times you'll see an interval, all right, where the solution is, where the differential equation is valid of an initial condition. So I'm going to find the general and then the actual. But we all have to start. What's the most important thing?
General solution or the general form.
Form. Got to start with the correct form. All right. Looks actually pretty close. Does anyone? Do you guys see what we need to do to fix this one?
Some math.
Divide by cosine.
I may want to make special emphasis. That derivative needs to be alone. All right, which means this is actually already on this side. Oh, that's good news. And that's already a mess, but that's over there, right? The G function.
That can be a mess.
That can be a mess, but it's over here. All right, we're gonna deal with that later. Okay, so only thing we need to do here. Divide this whole thing by cosine of x, and let's see what happens. Okay, so y, and I bounce back and forth pretty commonly between y and dy dx. Okay, so plus sine divided by cosine, so that gets tangent. Y equals, okay, one of those go away. Let's see, 2 cosine squared x sine x minus 1 over cosine secant. So that simplifies a little bit, I guess, on the right side. But not important at the moment. Most important thing right now is to do what?
Find your integration factor.
Integrating factor. Everything's all about that integrating factor. And I just always know it as t's, even though technically it's not t's here, it's x's, so we'll convert on the next study. All right, so e to the integral of tangent.
I don't mean to interrupt. If we were to accidentally put a t instead of x, would that be docking of points on a test?
Okay, we're gonna have so many variables. This is gonna, this is the official definition, which is always what I remember.
Yes,
But
sir.
I mean, we're dealing in x's,
X's.
and we're gonna so I'm gonna get to x's before I get it back in
So just
here.
long story short, make sure you have the correct
Yes,
variable.
have the correct variable because we just have so many.
Yes, sir.
And I was like, it's just something we want to focus on
Yep.
without a doubt. Okay, e. What is the integral of tangent?
Cotangent?
Is it secant?
You're thinking derivatives.
Okay.
Secant squared.
That's derivative. Do we remember how to everything with tangent?
Review trig identity.
With all trig functions, what do we always do almost every time?
Remember them?
No, just
Sine over cosine.
yeah.
And then we do the quotient rule, right? If we had to. I guess that works for derivatives.
Quotient
Yeah,
rule.
yeah. So integration by parts?
Easier.
U sub?
Use
The derivative of sine is co-negatives.
but we start with cosine, right?
Yeah, okay, because the derivative of cosine is sine.
Well, yes, they are always
Inverse
sine,
because one goes
sine and
negative.
cosine, one positive, negative,
Yeah.
absolutely. Du
that's ln.
Ah. Then this does remind me of one other little thing. I was like, could just because. So a negative out front, what does that do with logs?
It makes them like not happy, right?
No, that's fine. Is there a way that
It changes their order, like,
I don't know. Getting closer. You're thinking spin the log.
yeah.
Yes. All right. But
You can divide or multiplying is adding and dividing is
but I
subtracting.
prefer it if it was in here. How do I get it in here?
Do an E and do a power or what? I'm not really for sure what you're asking, to be honest.
Don't you just raise it to like the -1?
Yes. So ln of x squared.
Is
2 ln.
2 ln of x.
Yeah. So same thing. This is a -1.
So a -1 exponent on that cosine, so make it 1 over
Yes.
cosine?
Aha, yeah.
Okay,
That should just be.
yeah.
See, I was like, it's just so beautiful. Like, it was like, hey, and you know what? I blank on it all the time, but you know what I always remember? I remember how to find those. The toughest one, I believe is it secant? What's the integral of secant?
It's like 1 plus something, like 1 plus cotangent, 1 plus cotangent squared, or
No, the integral of secant, I'm pretty sure it's ln of secant plus tangent.
there it is.
And the reason I remember that is because when you prove it, you have to multiply it by secant plus tangent. That's the whole idea. Like, so if you know the fundamentals, you can always go back to identifying this, right? And here's the big thing: Diff Eq. So I said this on the first day. I'll say it again. I'm going to say it again and again and again. Diff Eq is actually easier than Calc 3. What we do in here, algebra, 90% of the time, and we do 2 integrals: U sub and by parts, because those are the 2 most common by a distance. Trig sub and everything else is way, way low on the list. But if you can do U sub and integration by parts, we get through almost everything. And then e to the ln of secant, what does this become?
It's just secant.
Secant. And so these are some of my favorites because how nice is this integrating factor?
Should be nice.
Really nice. Looking at what the problem is too, if I have a bunch of trigonometric functions here, if I had an e to the stuff, yuck. All right. But secant, I have a feeling this stuff's going to get real nice in just a minute.
I have a feeling.
Well, I was like, that's the point, right? You want to keep seeing ahead. Like because I can see in the beginning of a problem, like,
Why the tunnel's far away.
Take a breath. Like, but this one, I already know that I have a good feeling.
I got a feeling.
Let's see. Secant. Oh, actually, I just want to leave it like that. Okay, secant is one over cosine, so now this actually does that. Another one of those cancels out. Secant squared. All right, so multiply it through. And then we identify product rule. Is this the product rule right here?
I sure hope so.
Absolutely, right? What's the derivative of secant? Aha, see, so here, well, but that's but the point is right there. So I was like, ideally that should be in the recess mate, and you're like, oh yeah, because it's right here. I was like, it just
I'm
verifies.
trusting the gods on that one, so.
And actually, just as a note, what's our step after the product rule?
Integrate.
Integrate. Seeing ahead, right? What's the integral of secant squared? Okay, so that was done. What's the integral of this?
Is it a double angle entity? No.
Ah, yes it is.
Thanks.
What's the double angle of 2 cosine sine?
Sine squared or cosine squared.
Double angle, there's no squares.
Okay.
What is a double angle?
Cosine 2a or cosine 2x.
Yeah, 2x. And sine. This one's sine.
Okay.
But yeah, remember double angle means 2 times the angle, not
2 times the angle. Yeah.
Yes. So this right here, 2 sine theta cosine theta. That's sine 2 theta. So already seeing ahead, I was like, just to convert that right here. And that's the other thing, like, see, the whole point is the more math you do, the more math you see, right? You keep seeing your trig, you keep seeing your calculus. All right, now we're ready to integrate. So even though that started off as a mess, right? Piece by piece, right? The right side I'm talking about, right? Because seeing up here, this looks ugly, right? I don't know what that is.
Rob to the square on the cosine, sir.
The very first step was divide by
I
cosine.
get that. And now it's cosine third to cosine squared, but then down there you just have it as a cosine.
You're absolutely correct. Because I multiplied by secant.
Okay.
When I multiplied cosine
I see.
squared, that means divided by, so one more canceled out.
Okay.
This one increased. I was
I
looking
see.
at it further.
No, I just didn't distribute the secant through yet on my end, so that's my bad.
Yeah. No, I was just, as I was going, I was just multiplying it through that. Multiplying by secant means I was dividing by a cosine.
Yeah.
And then this one, it increased the power because it was secant,
Yeah,
the first power that we got secant
Yeah.
squared.
I feel you.
I was just doing my algebra plus my.
Mhm.
Oops, it's minus. So again, integral of sine is negative cosine, and then some reverse chain rule. And then integral of secant squared is tangent. So again, got all those to a simple enough form. One last step.
Divide by the integration factor.
You're absolutely correct, right? Divide by to what I was just saying. I mean, at this point, this is algebra. I'm like, I'm solving for y, so I just want to divide by whatever this is. But you're absolutely correct. That is the integrating factor that we started with. All right, and the secant is divided by a cosine, so. Oh, but it's
But
a
they're different.
it's a single.
Where's double, so you really can't do anything there, can you?
So all you can actually do is,
Keep it as it is, or
yeah, things like this.
there's nothing cleaner about making a cosine square in the bottom or, you know, that's, I was saying, unless you.
Divided by secant, that's 1 over, it becomes multiplied by a cosine, because it's 1 over, divided
one
by
over,
secant,
one
it's
over.
1 over, 1 over, yeah.
Cancels
So it
that.
actually becomes a multiply, so that's. Yeah, it does not combine into anything nice. And divided by secant. So that becomes minus sine. So that's sine over cosine, 1 over cosine, yep, sine. And then this guy becomes, yeah, 1 over secant, which is times a cosine as well. Okay, and then the step that is absolutely, in my opinion, the worst step, without a doubt. It's not even close, so I'm going to tend to skip it most of the time, just so you guys are aware. Is actually doing the IVP part. Because, right, I got to plug in pi over 4 in for all these x's, right, and then 3 root 2, and then it's just algebra fun. But you guys should be very aware of what is occurring, right? So the actual solution becomes actually came out to 7. Okay. It never comes out that nice.
Rigorous.
I get you. Just a little word, right? This is 3 root 2. Because at this point, yeah, because I have a bunch of root 2 over 2s.
I think with a 0, it happens right there.
Oh, okay, yeah. I was like pi over 2 cosine instead of pi over 2. Yes, that is X, so that is 0. Yes, you're correct. I was like, yeah, so, but it's still like,
It's still a mess.
I was like, we solve that down and you would actually get C equals 7, which is amazing.
Very lucky that it turned out that way. The power of 4 was a gimme. Synergy there.
Okay.
We have 5 minutes.
Okay, let's at least get this into the form, so we'll be ready for next time. In order to get this into the correct form, what do we need to do?
Get into the correct form. So divide by t, I guess.
Divide by t. That is absolutely correct.
So the integrating factor is going to be 2 over t. Or I guess the.
But I mean, the P of T.
Yeah,
Yes.
PUT, sorry.
But that's already good news because 2/T, what's that integrate to?
Natural log, right? So
Oh, well, look, so I have an E in a natural log, I already know, that's good news. See how we can see it from here? That's already gonna be a good problem.
just give us an A so we can walk out now, you know?
Yeah, I was like, see, that's like super awesome news. All right,
Doesn't get happier than that.
I was like,